My name is Shantanu Jathar and I'm an assistant professor in mechanical engineering at Colorado State University. The title of my poster is Emissions and Radiative Impacts of Sub-10 nanometer Particles from Biofuel and Fossil Fuel Cookstoves. This was recently accepted as a paper in Aerosol Science and Technology. This work was done at CSU and supported by Air Modus and Handix Scientific. Novel aerosol instrumentation has been used recently to measure particle emissions below 5 nanometers from both combustion sources such as IC engines and from traffic in near road source environments. All of these previous studies have concluded that not only do combustion sources produce sizable numbers of sub 5 nanometer particles, but that most of the number emissions are dominated by particle sizes below 3 nanometer. The table below highlights a few of these studies, and the graph shows particle number concentrations for 1 to 3 nanometer particles on the left and the particle size distribution over a much larger particle size range. However, there are no documented studies that have measured sub 5 nanometer particles from biofuel and fossil fuel cookstoves, an important source of fine particle pollution globally. In this work, we performed a study to measure particle emissions from cookstoves in the CSU emissions hood using the Air Modus A11, which measures particles between 1 and 5 nanometers, and an SMPS, which measures particles larger than 10 nanometers. We examined the emissions from 5 different cookstoves ranging from dirty to clean, a 3-stone fire, rocket elbow, charcoal gasifier, and a liquefied petroleum gas or LPG stove. The cookstoves were operated on a so-called water boil test that included a cold start, followed by a hot start, and concluding with a simmer for 45 minutes. We also measured CO2 concentrations to calculate emission factors for particle number. This example figure shows the number concentrations measured by the A11 and SMPS for the rocket elbow on the left and LPG on the right, along with the CO2 data. The N1 concentrations, or concentrations for particles larger than 1 nanometer, were larger than the N11 concentrations, suggesting that there were sizable emissions of sub-11 nanometer particles. The differences in N1 and N11 concentrations were larger for the LPG, shown on the right, than the rocket elbow, shown on the left. Finally, both concentrations were not significantly affected by the heating mode. This result figure compares the emission factors on a kilogram fuel basis for all 5 cookstoves. The N1 emissions were larger than the N11 emissions, as witnessed by the different y-axes in panels A and B. This again points to significant emissions of sub-11 nanometer particles by all cookstoves. When examining the emissions of sub-11 nanometer particles as a fraction of the total number, we found that cleaner cookstoves, shown in panel C, had an increasingly larger fraction of their particle emissions at sizes below 11 nanometer. The sub-11 nanometer particle emissions can be clearly seen in this figure that show the particle size distribution stitched together by combining the A11 data with the SMPS data. Surprisingly, all cookstoves showed the so-called nanocluster mode for 1 to 3 nanometer particles, which was likely composed of sulfuric acid and lower volatility organic compounds. Unfortunately, we did not measure the chemical composition of the sub-11 nanometer particles, but encourage future studies to do so. We used the emissions data in this work to inform the emissions of sub-10 nanometer particles in the GeoSchem global chemical transport model. Here we included emissions of the sub-11 nanometer particles for all combustion sources including fossil fuel and biofuel combustion, but not biomass burning. We used these GeoSchem simulations to study the number concentrations in the surface layer. While sub-10 nanometer particle number concentrations increased in source regions, as shown in panel A, there was a small impact on number concentrations for particle sizes larger than 10 nanometer, shown in panel B, and an even smaller impact on CCN relevant sizes, or cloud condensation nuclei relevant sizes, defined as particles larger than 80 nanometer, in panel C. This was very likely because those sub-10 nanometer particles were lost quite efficiently through coagulation with larger sized particles. Consequently, there was a minimal impact on the cloud albedo indirect effect. From the addition of these sub-10 nanometer particles, globally averaged, CCN sizes changed by less than 0.01%, and the cloud albedo indirect effect changed by 0.001 watts per meter squared. To conclude, the two key findings of this study are: Cookstoves emit more sub-10 nanometer particles than super 10 nanometer particles and emit more sub-10 nanometer particles than other combustion sources on a fuel burnt basis. Global chemical transport model simulations based on emissions data from this work and earlier work suggest that combustion emissions of sub-10 nanometer particles have little to no effect on CCN relevant sizes and any radiative impacts. Thank you for your attention, and I can answer any questions via email. Thank you.